Angie Ariza. I'm from Colombia. I'm a physicist and a data scientist. I started working. I mean, I just graduated and I went back. I went directly into the industry because I love programming. I've been doing a lot of things since I learned how to program. I've been working with classification problems, fraud detection problems. Right now, I'm working for a company called Happily, where we're trying to democratize funding. If you may have a great idea that you want to get funds for making it true, you can join us. Here is the link for Happily AI, and maybe we will have the opportunity that you are required to make your idea comes true. And I'm mainly working on a lot of prompt engineering and developing complete solutions for LLMs right now. So that's a little bit of my background. And since 2022, I've been a Women Touchmaker ambassador. I'm also part of Latinas in Tech and Women in Artificial Intelligence. So this is all to bring this community together. So this will be our agenda. First, I'm going to talk a little bit of machine learning. Then we're going to go inside of machine learning. Over these 3 points. What is the problem definition? What is that important? Data, just a little bit about it. Algorithms. Then we're going to see a little bit about the machine learning pipeline, and we're going to train a model. So I need you to come with me, try to answer the questions, and just don't be shy, and make all the questions that you may want to make. So first, a little bit of machine learning. Machine learning has different definitions. This is just one of the definitions you can find on internet or in books. This is the one we're gonna talk today about. So in last talk, you saw that artificial intelligence is a whole discipline itself. Right now, as we're gonna define machine learning in this talk, machine learning is a subset of artificial intelligence that enables computers to learn from data without being specifically programming to do so. So just think about it. We enable computers for learn from experience. Experience is traduced as data. So the data, whatever we put on that data is what the algorithm is going to learn, and without being explicitly programmed for, right? So under this definition, we can find at least two types of artificial intelligence. We're just going to center today on these two types. We have the supervised machine learning and the unsupervised machine learning. So first, to talk about supervised machine learning, it's like the name came for think that we have a supervisor. We're watching exactly what are we training, what is the data, and what is the result that we want. This is the main part of this kind of learning. When we train some algorithms in supervised learning, we already know what will be the result. We know what is the thing that we're looking for. So in this case, something really important, the data that is going to feed the model has labels. I mean, we already know that this is a cow, this is an elephant, and this is a camel. We already know that is the name for this image in this case. And at the end of the model, we want the same result. So wherever we pass an image, we want the result to tell us if it is an elephant, is a camel, or is a cow. So we are the supervisor that we are saying the algorithm, okay, with this data, I want you to learn specifically the labels. And I want you to become very good of classifying whatever I just gonna enter as a new data to the algorithm and give me the response that I teach you that I want to have for you. So I want to have a tag if it is that tell me if it is an elephant, a camel, or a cow. So we already know all the process, right? This is very important. So we have labels. We already know what will be the result that we desire. And on unsupervised learning, on the other side, there is not supervision. There is not a supervisor that is seeing how is the data and already is telling the algorithm what is the result that we want. This one is my personal favorite kind of learning because we're just trying to see what are the patterns inside the data without telling the algorithm exactly what we want to see, you know? So in this case, we don't have labels. We don't just have some animals randomly. We train a model, and the model is giving us some groups, but we didn't specifically ask for the classification of the groups. It could be because these animals have feathers, these don't have feathers, and these have other things like fur. But we don't know. We don't tell the algorithm specifically what we want, what we need. Or it could be because these don't have any paws or like legs. These have four paws or legs, and these just have two. So we're not specifically telling the algorithm what are the instructions that we wanted to follow to give us an answer. It's just finding some patterns, and we're responsible to go again over the algorithm, clean the data, and trying to make them as clear as possible for the algorithm to help us with the solution that we might require. you know so this is the basic difference. And here is another example. If we can compare in a similar exercise the two kind of learnings. So we have the supervised learning. We have here the labels. This is a dog, this is a dog, this is not a dog, not a dog. The supervised algorithm and the prediction. So wherever we enter a new image, we want the algorithm to tell us if it is a dog or is not a dog, right? So that's supervised. And on the unsupervised algorithm, in this case, we have some images. We're not saying specifically if it's a dog or not a dog. Maybe it could be if it has feathers or not. We're not telling specifically what we want. And at the end, the algorithm is just grouping all the examples that seem similar or have something in common, depending on the pattern that it found, right? If you have any questions, you can add it at the end, in this case, just for the part of basic machine learning. So till here, as the thing that I want you to focus on is you can see that the algorithm in itself here is not important. What is important is how is the data that is entering into the algorithm, and how is the result that we need from the algorithm. You know, I know this could sound obvious, but obvious is not a scientific concept, so we can ignore them. Or maybe we sometimes we get used to ignore or just say that something is very obvious. But the thing is that here is when the critical thinking is dying right now, because we tend to just think that it's naturally or is obvious. But the thing is that in the detail is where the algorithms work or doesn't work for a specific solution. So in this case, I want you to center on the think how is the entrance and what is the result that we wanted from the algorithm, right? So this is the most important thing on the definition in machine learning, right? You can read a lot of information about that, but this is going to be critical. So passing by for the next part, we're going a little bit inside the machine learning, right? Not just the type of learning. So first, I want to talk about the problem definition. In this case, we have this image. We have like a dog with a costume. Maybe it's like a plain costume. Apparently, we have this model that says it's a 99% frog. So I want to ask you. You can write on the chat, and I'll be reading your answers. Does the model works? What do you say? Okay, somebody said the model doesn't work. No, it doesn't work. Yes, yes. It's like a frog, dog, airplane thing going on the image. Yeah, some other answer. Who will say it works? No, needs more trained data. No, it needs more trained data. Maybe, maybe. Words for that. I like that answer, Diana. Unless the dog is called Frog, that's a good one. Yeah, it's nice. It's nice. It's very funny. It's very funny. I don't know if you saw this image. Was very viral on LinkedIn last year. Because people was talking about that. Does the model work? Does the model doesn't work? Um, I wonder why it isn't recognized as a plane. Yeah, that's a good answer. That's a good answer. I like that too. So let's pass to the next slide. So the thing is, we can say, right? We can say. I like one person said something like that. But the thing is, what was the purpose of the model? Maybe the model is correct. It has to identify dogs and said it's a frog. So in that case, it's great. It's doing its job. Other things, what is this 99? Is 99% of what? Position, is recall, is what is this measuring, you know? What is the scope of the model? Maybe the model was trained only on frogs, not on dogs. And in this case, the image, the dog is the closest to a frog that the model could find, you know? So we don't know. Maybe we're just asking the model a question that is not meant to respond. So in that case, it's our fault. If the model maybe is a good model, it works. Is this model better? I mean, 99% respect to what? What will be the benchmark? You know? So the truth is that we don't have any of these answers. If everyone came proclaiming that its model is the best model in the world to identify frogs with this image, is like, okay, I will need more information about that. Or if I'm saying that it's true, is my model is really good looking for frogs, but somebody else just test my model, sorry, with with this image, and it's saying that my model is not good, is also not true. So what is the scope? So it's really good, like being very critical about, okay, people is saying that that kind of model or that tool doesn't work. Okay, why is they saying that? They did that did they test it very well or not? Maybe they're asking something to the model that is not meant to be, you know. So this is the first thing. Problem definition. We need more information. We need to know what was the model, the purpose of the model. Yeah, what is the scope of the model? Is this model better or bad? What will be that? We will need a benchmark, something to compare the model to, right? So some of the answers were really good. It's always like be critical. Yeah, be critical. First, what is the model for? Then we have the data. Data is crucial, you know. And in this case, I just want to show you this image. This is the multimodal learning. You will hear beyond the supervising and unsupervised learning, we have a lot of more knowledge today. But if you understand this basic, you will understand the rest. So in this case, we have multimodal learning. This is about the modes of the data, because I mean, we can have the same information, but in different ways. You know, we can have the information by text, we can have by speech, we can have it by images, we can have it by, for example, it's not the same if we say that, I mean, we're talking about certain subject, but we're talking in English or in Espanol or in French, you know, or also in sign language. I mean, would it be? It could be the same information, but the way we're reading information, we're comparing the information is different. So that is very important for models. Sometimes models are just meant to understand certain kind of data, and they're just meant just to give the result in that specific type of data. You know, so that is that this is a like an edge case. The multimodal learning is an edge case. It's an edge case. But I don't want to go through because usually people shows the ethical um, problems with the data. For example, okay, we train a lot of information on faces, but just white faces. But I mean, that's another edge case. The thing is that every day, every model is trained with certain kind of data, and we just use the model. But sometimes it's like, okay, the model is wrong. Maybe the model is not wrong, but it's not meant for that data. And that is when it's very important to be very critical, to be very diverse. We need all the different point of views. We need all the women, all the men, of course, all the races, all the different looks, or we need all the LGBT community, because that way we can have better data to feed our models, you know. you can see, I mean, the hidden problems inside the data if you don't see the prejudices, for example, or the biases. So it's very important to work in as a team to work on clean and good data for our purpose, the purpose of our model specifically. So here are some questions for that. Which data was it trained on? You know, which kind of data? How good was the data? The data quality? How diverse was the data, depending of the results that we want? You know, how is the nature of the data? And this is very important. For example, whenever we work on fraud detection, I noticed that we're trying to detect the fraud, you know, but the fraud changes itself and changes very fast. How fast may it change? It's different for the different kind of changes. So, for example, in Colombia, for anti-money laundering, there is a law that says that you need to retrain the algorithm and not an unsupervised learning algorithm every 6 months maximum, because based on their experience, every 6 months, the nature itself of this kind of fraud changes and changes a lot. And it's 6 months is a lot of time. What we notice, it changes more fast than we can change or improve the model. You know, so this is very important because sometimes it's okay. I'm trying this model, but this model is from 2 years ago. 2 years ago, I think it's not. It's been a lot of things happening to trust in that model. You know, so it might depend. What is the nature of the data that train the model? You know, so other question will be, was enough data to support trustable results? Trustable results will be for the results that I need, you know, for my problem. It's always good to ask that. Also, is that what is the scope of the data? As we saw here with the dog frog, is the model maybe its purpose is to identify every living thing or just frogs, or what is happening here? What is the scope? And also the type of data also matters. I mean, it's crucial right now that we're seeing all these amazing models that receive different kind of data, but it's like, okay, is it good if I maybe it's a model that is trained over images, but the images could be, I don't know, this is a thumb, but it's also a one, or it's also, it's saying like it's okay. What is the real information we're taking for the same kind of data, right? So this is very important. And passing to the algorithms, just look at this. We have like, okay, these are some algorithms on supervised learning, and these are some other algorithms in unsupervised learning. You can see that the algorithms work differently for the data. You know, this part, this is data. So some algorithms are very good for this kind of data. This continuous data is numbers essentially, and this kind of algorithms work for categorical data that will be, for example, words or labels. You know, so we have the different types of learning. We have different algorithms, but not all algorithms work the same for the same data. So data is crucial. It will define which algorithm I'm going to use, what will be the result I'm expecting, how many times I need to train my model. You know, so data is the most crucial thing in this part. And now, passing to algorithms, I want to show you this. This is just an example. In this case, it's just one kind of algorithm. Let's go back here a moment. On the unsupervised learning, we have, for example, clustering. Clustering is one use case. Clustering was this. We just have some data without labels. We have all algorithms. This will be a clustering algorithm, for example, and it will create clusters or small groups, right? But we're not telling exactly what we want to see. It's just creating these groups. So here on the clustering, we have just in clustering, in this case, we have 6 types of clustering algorithms. So the nature itself of the algorithm is different. We have clustering based of centroids. That will be the distance between the points. We have clustering based on connectivity, on density, on graphs, on distribution, on comprehension. And this is really, really interesting. For example, most of the time, different areas tend to use the same kind of algorithms because some algorithms work better for certain kind of problems. So for example, you may hear that people who is working on drug detection or healthcare are always using the same kind of algorithms because they work very well for that data. And the people who are working on fraud, for example, they tend to use always the same algorithms because they work very well for the data. So the kind of data, the nature of the data will define the algorithm that they're going to use. Also the experience, this is very interesting because at the end of the day we're humans who are building the solution. So most of the time, different algorithms can give us a good result for the same problem, but which one we're gonna choose, we tend to choose the algorithm we know better, because that way we can interpret better the results, we can work better with the hyperparameters of the algorithm, and that's good. You will see that when you see the solution, you can in certain way you can see the people who work behind it, and that's really nice. That's really human itself. So right here at the right side, we have two algorithms. This is clustering and clustering. It's the same kind of algorithm. So we're trying to look for these clusters, these little clusters. But depending of what I need as a solution and how is my data, I'm going to choose one algorithm or the other. So this one that looks like a happy face is the BDS scan algorithm. And the thing with this algorithm, for example, is that it's a density base. So it will create these clusters based on density. The hyperparameters for this one is okay. It will start at some point. It will measure how close are the neighbors based on a distance that I'm gonna give it, and how many neighbors am I going to consider as a cluster. So that's the way he's choosing all the red points to be just one algorithm, later all the yellow points to be an algorithm and a cluster, the yellow points to be another cluster, and the blue one and the green one, right? That's how it works. And the other image, this image, is another algorithm, is the k-means. This is based on centroid. So in this case, it starts with certain points. It's measuring the difference, the average distance between a center point that is going to iterate with, and the distance with the rest of the point. So how can I choose one algorithm over the other? It might depend of the solution that I want to build and the data I have to work on, right? So that is really important and really nice to see. So here is another example. In this case, this is a classification model, and we have different algorithms. We have a CAT-boost, a LGBM, and SGBoost. Maybe you have heard of these algorithms because some of them are very popular, and they are popular for certain reasons, and they're very good. So you can hear over and over again that people is talking about SGBoost because it's a very good algorithm for certain use cases. For example, in this case, so we train this model with certain data, and we train another couple. We train for the same model, but I added in this case a new metric. But in this case, is this the best model? I mean, what would be the best model? The best accuracy, the best recall, the best what? It might depend again of what I need. So it's not easy again just to say because we have the frog dog with 99% of something. It's good respect to what. So it's always important. Okay, you're telling me you're having a high accuracy. Is that good? It might depend of the problem. So always asking that. It might depend. What is the scope? How was it trained? What it was trained for? And in this case, for example, is this the best metric? We have a 94% of accuracy. That sounds really good. But in this use case, when I added this new metric, a profit that was specific for the problem that I needed, profit will be more important than accuracy. So if you can see in the first image, the best model was the CAT-boost model, algorithm. And in the second image, the best model was a light GBM. So how can I choose is the best model for my solution? It might depend on what I need for my solution, right? So again, it might depend. I will need to know more about the solution, what's the problem, what the solution for, what was the scope, the same kind of questions. And now, oh, I thought if I have another slide here. And now, just if you see, we're talking just about um, the problem definition, the first part. Then a second part, there is the data, and then the algorithm. Just these three parts. But the thing is, this is like this is also a very simplified machine learning pipeline and has more steps. It's not just problem definition, data, and algorithm. In this case, I just want to think about this. Most of the time, we tend to think that a machine learning pipeline will look like this. It's like we have the same effort over the time, and we have like several steps. In this case, we have a problem definition, all the data, and the data will be the cleaning, the feature engineering, yeah, just leave it. The analysis, the exploratory data analysis, and all the model. We have to choose the model, to train over the model, to evaluate the model, for example. Then we have the deployment of the model. And most of the time is, okay, do we have all the requirements for a model is going to be fit correctly? Are we gonna evaluate? Are we gonna monitor it? You know, and finally the results and how we need those results. You know? But the thing is that it's not a continuous line like this one. Oh, this was the slide that I missed. Most of the time, it looks like this. It's like a mountain. This will be time and effort. So when you're working on a machine learning pipeline, sometimes you will spend most of the time on the problem definition and less of the time and effort on the data analysis, on the choosing the algorithm. But this changes over the iterations of the solution. You know, so maybe in the second iteration, the problem definition is not so important as it is the data analysis or choosing the right algorithm, right? But even that this look a little bit more complete, the thing is that it tends to look more like this. So we start with the problem definition, but you can go back many times just to review over and over again. Do we have enough um, uh, sources to solve the problem? Do we need to solve this problem? Do we need machine learning to solve it? Can we solve it in another way? What would be the best way to do it? What would be our scope? And then we go to the data. Okay, we have this data, we have to clean it, but after cleaning it, it happens that we don't have enough data as we think we have it, or maybe we have enough information, but not for the problem that we was defined, or we was trying to solve. So we go back again, review over and over again, and this is all I mean, it's more a realistic way of seeing how is a machine learning pipeline. And even sometimes the the solution didn't even go to the end. Sometimes you can come here, have a whole problem, good definition, you have the whole data, you're choosing the algorithm, iterating over it, but it happens that maybe it was not required. We can solve the problem without machine learning, or the problem wasn't what we needed. We think we need to at the beginning of the project. So it happened all the time, right? Just to have it in mind. Whenever you see a product, a machine learning product, there is a lot of work behind. And the thing is, be critical about it, because you can be critical in each part of this process. I mean, the problem definition, how was the problem definition? What is the solution for? How is the data? How is the data quality? Why did you choose that algorithm? How the algorithm work? That right now, this part is having a lot of attention, but each part is very important. How do you deploy the model? Because maybe, I mean, it works very well here, but in the real world, it's not working as good as it should. And the results, are the results answering the questions of the problem definition? Are we using correctly this tool, for example? So always being very critical about it. And now I want you to join me to train a model, right? So I'm gonna share with you an open tool that is very good to train images. The idea is we're gonna train a model to classify my hand, saying if it's thumb up or thumb down, right? So I'm gonna open the tool here, but I have to stop sharing and reshare because it's opening in another window. This is called Teachable Machine. Is free. I just gonna share with you the link. This works for training images, but also well, for training, I think, movement and speech. You know. So in this case, we're gonna train two classes. The first class, I'm gonna add a name, will be thumbs up, and the second class will be thumbs down. Now, yeah, that's great. And we're gonna start with the camera. Every time I push this button, it's gonna take the images. So I just gonna hide a little bit and yeah. So that will be my data to thumb up, and we're gonna add the data to thumb down. So let's see that I don't wanna be seen here. Yeah, that's right. Now we're gonna prepare the model. It's being prepared. This is very good because at the end we can even export the model. You're going to see. Here it is. We can start. Okay, we can export it. Not right now. So in this area, it's going to tell is if it is a thumb up or thumb down, right? So let's try it. Okay, it's thumb up, right? Nice, nice, really nice, and thumb down, 100%. That's good. That's good. So we can see what happens if I shows. It's a little bit confused. It's still seeing the thumbs. It's not very good. Can you see it? The thumb is up, but the classes is saying that thumb is down. Right? Right? Okay, let's go make something very clear. So here, thumb up, 100%. Thumb up. Let's change a little bit. Here, thumb up, thumb up. What happens if I do this? Okay, it's still okay there. Can you see it's changing between thumb up or thumb down. Can you say what is this happening? What do you think? Please let me know right on the chat, or if you might want to talk, if you're super welcome. What do you think is happening in this case? Right, I want to see it. Do you have any clue? What do you think could be happening? I mean, here is a clear thumb up, right? It's saying it's 100%. But what happens if I put it in some other here? Why is not a thumb up, right? What if I do this? Okay, it's still giving me a little bit of thumb up. What if I do this? Okay, it's 100% thumb up. Here it's a little bit confused, right? What do you think is happening in that case? Okay, we have here some message. Okay, it says no diverse data. Other fingers appear. That's correct. Not enough visual data. Fingers are showing off. Yeah. The angle of the hand is confusing it. Yes, that's correct. Other fingers. Yeah, data diversity. So yeah, you got it. The thing is, I train the model just with certain data, but I avoid some parts. So I didn't add any data like this. Yeah, it's a thumb up, but I mean the model, as you can see, is not meant to predict a thumb up if I passes my whole hand, you know. And in this case, for example, if I didn't add the thumb up, I just say, okay, this could be one. So in this case, even though that is giving me the result that we needed, the model wasn't trained to say that this is one. This is the one thing or the number one. This is a thumb up, right? So we need to add that. So let's add more data and see how it works. Let me go this to here. What is the part that is not working better? Okay. That this way. Now it's working there. Okay, okay. So let's add more data here. Yeah, that's correct. Okay, prepare the model again. It's being prepared. Accept. And let's try it now. So it's 100% thumb up and in every corner, right? What happened with the thumb down? This is still working. What happened if I add my left hand? Okay, okay, no, that's not a thumb up. Not, no, so bad in this case. They didn't like my left hand. So yeah, we will need to retrain this model, right? But that's the great idea. So I'm very happy that you got it and you got it very fast. It's about the data in this case. I mean, what is the model meant to? It's meant to predict thumb up or thumb down, right? But how is the data that I fed into the model, right? So all are the questions that we need, and this is very important. We need to be very critical about machine learning more now more than ever, right? So other interesting here that you can see later is we can export the model, and we can have the model in JavaScript. We can have it in Python here as a keras, and also this light version of TensorFlow. I think I don't know, this needs something more to work. But for example, I think there are so many ways that using it, because you already have it pre-trained. So you can copy, for example, the JavaScript version and using it in a web page code, and in P5 I've using it, and it's very nice. So for example, in this case, I use it as thumb up, as thumb down. But for example, we can reuse this model to give us our results. For example, every time I add a thumb up, I want to give me happy face, or say that is correct or not correct. So that way we can complete, yeah, like create a whole solution that based on the model I want you to do this other thing, just to show you that the other options that we have now. As a conclusion for this talk, I really want you to keep in mind the critical the thinking, um, and there are some little tips I may want to share with you. So please always remember, a scientific solution that is not magic work inside a framework. The framework will mean that the model always has a scope, and it will work well inside that scope. You know, we have to focus. I mean, we have to know what are the problem, what is the focus for the solution. What was the problem trained for? What were the conditions? And the conditions could be just a few conditions, like, okay, this model just work for thumbs up and down. That's really few conditions. Or is a model that can work for thumbs, but also understand if I have a draw of my thumb, or maybe if this is a thumb, but it's also something in sign language, but it understands because it was trained for that. It already have all the context and have all the right data and the right information for that kind of solution, right? And always data is crucial. I mean, you can hear a lot of ethical implications, and that's an edge case. But most of the time, the details are in that case, because you can buy a tool. It tells you that it works in certain way, but it's not the tool that you might need, and that difference will be on the data, right? And now, yeah, if you have some questions for me, that would be nice.
Yeah, if any of you have any question, feel free to put it in the chat. And if you found anything you learned very interesting from today's session, also please leave it in the chat.
I see one question. It says what algorithm do you use for thumb up or thumb down? I think it's for default is using a neural network in Keras. Right. I mean, this should be pre-trained. So I'm not sure if they're using ImageNet or some flip image. The neural network is already pre-trained. I just added new data. and a specification for classification in this case. Just two classes, because we can add many classes in this case, but this tool already understands that, so every time I just choose to add a new class, it's already understanding that I'm adding a label and a new class, and I might require that class as a result. So I think I mean, obviously it's chaos, but the algorithm is a neural network that might be pre-trained or on ImageNet or something like that.
We have another question. Someone asking, which is a recommended path to begin learning in machine learning?
That's really good. It might depend of your way of learning, and that's not a simple question. It takes time for you to understand if you learn faster just being hands-on, or maybe you need someone to explain to you, or you're better reading, or you're better following a video, or you're better at seeing certain kind of courses, and you will notice that you learn better for. I mean, if the course, for example, even if it's in English or in Spanish, or if the course is, I see the theoretical part, and immediately I go to the hands-on, or maybe not. For me, it's just going through all the theoretical part, and after that, starting to going hands-on. So the most important is to learn what works better for you, and after that just eat it all. Like, don't contain your curiosity. It's very good to be in a community, like to talk with everyone, because all the time there are some new things very fast, so that way you can keep updated, you know.
Thank you for answering. Another question from Yash is, can you tell us one most advanced application of machine learning so far, and something that's really interested you in this year, in 2024?
There is a lot, and I've been I'm very critical all the time, even with the things that I like the most, and even it's because of that, because I want to live in the future. I want to bring uh, um tourism to my time. I don't want to wait till I will have the best algorithms and all the artificial intelligence. So there is a lot. I recently saw the intelligence assistant from Rabbit from Rabbit or mRabbit. I don't know if you've seen it. I mean, right now, what is very interesting is the multimodal learning, because if you see in Gemini, I mean, I try to speak different languages. I can communicate depending of my mood in Spanish, if I angry or very emotional about something. If I'm professional, I communicate there in English. My sister is half deaf, so I know a little bit of sign languages. So just speaking or communicate just in one mode is too limited for me. So whenever I see all the new technology that it's used in multimodal languages, is very interesting and very needed, because at the end of the day, we need technology to help people. If we can help the people that need it the most, we're not working well, you know.
Makes sense. Diana is asking specifically, what kind of ML application have you ever seen in supply chain industry?
Creativity could work very well. I've seen. I mean, I don't know if you. I mean, this is not supply chain, but sometimes we were trying to predict forecasting. We're trying to predict whatever the stock for certain kind of food that will be rotten in a short time. But just reading, doing my research, I found that we can solve forecasting for doing clustering, and I have never thought of that. So the thing is, it might depend on your experience and your knowledge and your creativity. You can create very good, innovative, and creative solutions, even if, I mean, something that you could not imagine and no one has seen. Because I mean, the nature, the problem is there, and you just need the data. You need to be creative, and you need to have more experience, and just implement a new solution. So I've seen different things. I don't remember one right now specifically for supply chain, but there is different ways to solve the same problem. So I will encourage you to always think of the way that works better for you or your creativity, you know.
Makes Thanks. Thank you, Angie. I'm gonna reshare my screen. We want to thank you for we want to give you this certificate of appreciation. Angie, thank you so much for hosting this session, and it's definitely wonderful to have you here. And thank you for your time and commitment. For the next thing, I want to mention that for everyone who is attending today, please mark your calendar for our next session, which will be on March 27th, 7 p.m. Toronto time. And since due to the change of our Zoom account, um, we are changing our Zoom account. So if everyone could re-register through the link, which I think Maria just shared in the chat. If you could re-register through the new Zoom link, that would be great. And please follow us on LinkedIn and join our community if you want. Also, we have a monthly newsletter. Please feel free to subscribe it. And if you have time, please complete a quick survey, which I think Angie also shared in the chat. So the last thing is I want to have a big shout out to all of our volunteers. We cannot deliver this session without you guys. And thank you all for all the commitments and time. Thank you. And also thank you all for joining us today. It's really nice to have you, Angie, and have everyone here. So thank you.